Chapter 2, Linking Quality and Business. In this chapter, defining the voice of the customer through specifications, understanding the basis of true quality, recognizing that the quality of a system's individual pieces aggregates to form the whole, introducing the Sigma scale of quality. You make judgments on what is and what isn't good quality all the time. For example, you recognize when you eat a lousy sandwich or when your cell phone provider has bad service. But in the world of Six Sigma, quality is a deeper topic. To understand quality in Six Sigma terms, you need a transformational definition of what quality actually is. You can thus use that definition to guide and gauge your work activities. In the end, how closely you adopt this definition of quality largely determines the viability of your improvement efforts. In this chapter, we cover quality, how customers drive it and ask for it, what it looks like, and how to rate it. The discussions here give you a good grasp on why quality matters so much and prepare you to strive for the best. Specifications. Listening to the voice of the customer. When you buy a Coca-Cola, you, as a customer, expect a certain experience. You expect your experience to be the same each time you open a new can. If the drink had too much sugar one time, or not enough secret ingredient another time, you'd notice and feel dissatisfied. The Coca-Cola Company knows this fact about you, its customer, and so it very carefully controls the amount and makeup of each ingredient going into its drinks. The way Coca-Cola controls its product and your experience is through specifications. Each specification represents what the customer requires to be satisfied. In this section, we explain how to set specifications appropriately. How close is close enough? Understanding the need for specifications. Before the 1800s, all products were manufactured one at a time by craftsmen. A gunsmith, for example, would shape a single barrel of a gun and then expertly carve a single wooden stock to match the barrel's dimensions. The pieces fit together because the craftsman adjusted each part to match the other. A revolution was ignited when specialists began to separately create each of the components of a product. Because the specialists each focused on a smaller area, they became more expert and efficient in producing that piece. The overall result was an economy that produced goods and services much more quickly and at a much lower cost than before. It was in this environment of economic revolution that specifications were born. Getting Billy Bob's barrels to fit into Cletus's wooden stocks required some formal coordination. Specifications told the specialists what size or shape to make their parts. That way, when all the separate parts were assembled together, they would still fit. Defining specifications. A specification is the value separating acceptable from unacceptable performance. You probably consider spending more than $200 a month on movie tickets unacceptable for your personal budget. But what about $100? $50? At what dollar value is movie ticket spending acceptable or unacceptable? That's your specification. This definition holds for all process or characteristic performance measures. You can find several different types of specifications, several of which are shown in Figure 2.1. Right there. Specification limit, or SL. Any value designating acceptable from unacceptable performance. One-sided specification. A specification limit that designates only a single transition point from acceptable to unacceptable performance. For example, if you care only that the characteristic or process performance not exceed a certain upper value, that is a one-sided specification. Two-sided specification. A pair of specification limits creating an interval of acceptable performance between two limits. Upper specification limit, or USL. A value designating an upper limit above which the process or characteristic performance is unacceptable. Lower specification limit. A value designating a lower limit below which the process or characteristic performance is unacceptable. And target, or T. the single designated value you want the process or characteristic to perform at. A specification target is an ideal. Variation prevents the process or characteristic from exactly hitting the target every time. If set up correctly, specifications represent the range of values at which a characteristic is still acceptable to the customer. Often, customers aren't directly involved in your work. You never directly interact with them or see them, but a characteristic's specification is always available to you. In this way, specifications are said to represent the voice of the customer, or VOC for short. Do you do the rumba, creating realistic specifications? You should never create specifications arbitrarily. Unless they actually represent the values that separate good from bad performance, specifications become a stumbling block to progress. If you set a specification too loosely, your customer will be dissatisfied or upset with the performance of what you provide, even though it meets the specification. If a specification is set too tightly, you spend more resources than you should to always perform within your overly narrow goalpost. Imagine a specification requiring a delivered pizza to be between 120.4 degrees Fahrenheit and 120.6 degrees Fahrenheit when it arrives at the customer's door. To be within this required temperature range, the pizza company would have to take some pretty complicated and expensive actions. Maybe they'd have to use space-age ceramic pizza boxes made out of space shuttle tiles. In any case, meeting that specification would take a lot of work and expense. But do customers really require this extent of control over the temperature of their pizzas? Probably not. A less troublesome specification, and one just as satisfactory to the customer, may be 115 degrees Fahrenheit to 125 degrees Fahrenheit. Six Sigma uses a mind-jogging acronym, RUMBA, R-U-M-B-A, to help you evaluate the appropriateness of any specification. R for reasonable is the specification based on a reasonable assessment of the customer's actual needs. Does the specification relate directly to the performance of the characteristic? U for understandable. Is the specification clearly stated and defined so that no one can misinterpret it? Measurable. You can measure the characteristic's performance against the specification. Can you measure the M for measurable. Can you measure the characteristic's performance against the specification? If not, a lot of debate will ensue between you and your customer as to whether the specification has been met. B for believable. Have you bought into the specification setting? Can you and your coworker peers strive to meet the specification? Attainable or achievable? A for attainable. Can the level and range of the specification be reached? You need to review each specification to make sure that it passes the RUMBA test. If it falls short in any of the RUMBA categories, begin to develop a plan to bring the rogue specification back into control. Very often, an improvement project is fast-tracked or solved through a simple RUMBA review and adjustment of the involved specifications. The performance of the characteristic or process never has to be changed. Always review the appropriateness of specifications early in your Six Sigma project. Examining what quality truly is. To begin understanding the technical side of Six Sigma, you have to first answer a seemingly straightforward question. What is quality? A traditional and widely held definition is quality equals compliance with specifications. The following mental experiment walks through the traditional definition of quality and highlights why measuring quality this way is a flawed approach. Figure 2.2 shows an important characteristic of a process or product. Any characteristic that is critical to your customer. The horizontal axis of the figure represents the scale for the measurement for this critical characteristic. It may be the diameter of a part in inches, the cycle time of a process in seconds, or the cost of a service in dollars. Whatever characteristic is critical to your customer. The target, T, and upper and lower specification limits, USL and LSL respectively, are also shown for this characteristic. Now imagine you come across 4 parts that have come out of this process. You measure each one for how it performs on this critical customer characteristic. Part 1 measures far outside the allowed specification window. Part 2 is just outside the allowable window by the smallest margin possible. Part 3 is just inside the allowable window, also by the smallest of margins. And Part 4 is nearly right at the ideal target value. Deciding which of these 4 parts has the worst quality, which one you never want to get into the customer's hands, is pretty easy. Part 1 is clearly the worst, and picking the highest quality part is easy. 2. Part 4 almost matches the ideal target value from the customer. From the customer. But what about parts 2 and 3? Which of these 2 has higher quality? Remember, part 2 is just outside the specification limit. Part 3 is just inside. Does that mean that part 2 is bad and part 3 is good? Think of how these 2 parts will perform in the customer's hands. Part 2 will definitely fall before part 3. Will part 2 definitely fall before part 3? With only the slightest imaginable difference between parts 2 and 3, do you think the customer will perceive a difference in their performance? The answer is no. From the customer's perspective, parts 2 and 3 are the same. And from your perspective, the producer's perspective, parts 2 and 3 don't present any tangible difference in warranty returns or the cost of lost customer loyalty. So even though one part is within specifications or in spec, the other is out. No difference in their quality really exists. Ford's hard lesson. In the 1980s, Ford Motor Company had a wake-up call about its understanding of what quality is and isn't. Back then, its Batavia, Michigan plant religiously followed a quality policy based on the belief that compliance with customer specifications was what defined a high-quality product. Make the part in spec and it would be good. Make the part out of spec and it would be bad. Ford made sure that its operating policies and procedures were set up and that all its employees were trained so that nothing was allowed to advance in production or to leave the factory unless measured proof indicated that the characteristic was within the required limits. At this same time, Ford was working with Mazda in a joint venture. Both companies produced the exact same automatic transmission from the exact same blueprints with the exact same critical characteristics and specifications. Ford transmissions went into their Probe vehicles, while Mazda's went into their MX-6S vehicles. You may remember these cars. I do remember Ford Probes. As both companies built transmissions, and as reports started to come back from customers, Ford began to see a stark difference in the data. Transmissions Ford built were several times more likely to have a problem and require warranty service than the same transmissions built by Mazda. How could this discrepancy be? Ford had never worked harder to make sure every critical characteristic was within the required spec limits. It had hardly followed its quality procedures. It had strictly followed its quality procedures and had made sure that no parts exceeding the spec limits ever left the factory. Why then were Mazda transmissions so much more profitable? Ford had to know why, so it acquired several transmission samples, some from its own factory, some from Mazda, and began tearing them apart and studying them to find the root cause. First, Ford compared the transmissions for vibration. A good transmission with high reliability runs smoothly with little vibration. In the tests, Mazda transmissions had vibration levels so much lower than Ford had ever seen that Ford first thought its vibration test equipment was broken. But the tests ended up being accurate. Mazda's transmissions just ran that much more smoothly than Ford's. The folks at Ford also did dimensional checks of what all the transmission's critical parameters, What they found was that the distribution of measurements from the Ford samples did meet the goal of being within customer specifications, but the variation in the parts used up the entire width of the spec window, with just as many parts near the edges of the spec limit as were in the middle. Mazda's transmissions, on the other hand, showed a marked difference in consistency. All of their measurements were lumped at the center of each spec, always very close to the ideal target value. Ford quickly began to understand the reason for its lower profitability and performance. The quality it sought didn't come from just getting in the spec window. Instead, Ford found that quality sprang from working to get all the parts to be on target with minimal variation. Ford's chief of operations even published an internal video of the findings from the study. In it, he admitted that Ford's quality policy and procedures had been wrong, that its very own policies had led to the poor quality and business problems it was experiencing. This painful experience was one of the things that motivated Ford to change the way it thought of quality. Contrary to the traditional definition, quality is not equivalent to a part's or process's compliance with specifications. A better, more realistic definition of quality is quality equals on-target performance with as little variation as possible. This definition of quality is so important because, in reality, quality problems increase more and more the farther and farther the performance strays from the specified ideal target, even while performance is still within specifications. Using the true definition of quality, you can see that the target, not the limits, is the most important part of a specification, and getting a characteristic to operate on target with as little variation as possible should be your focus. Discovering the cost of poor quality curve, football, and Taguchi's loss function. What's poor quality really costing your business? Figure 2.3 graphically compares the flawed traditional perspective and the Six Sigma perspective on specifications and their relation to quality and costs. Traditionally, companies have thought that quality is like kicking football field goals. As long as the ball goes between the uprights, you get the full 3 points regardless of whether it goes straight down the middle or it hits the upright and bounces in. This goalpost kind of thinking is the traditional perspective shown with the specification in figure 2.3. The thinking under this mentality goes that when a critical characteristic lands inside the spec limits, it adds no additional costs to the company. But when it falls outside the specs, the company incurs a fixed cost, such as for repair or replacement, or for lost customer loyalty. Unfortunately, this goalpost definition of quality costs just doesn't match reality. What actually happens is that costs begin to increase with any deviation from the ideal customer target, even while the characteristic is still in spec. These incremental costs, such as disrupted production flow, increased inventories, incrementally reduced product performance, and lessened product reliability, usually aren't accounted for immediately, but they always occur eventually. And the farther the characteristic gets away from the ideal target, the more and more it costs the company. The cost quality curve is the Six Sigma perspective shown in figure 2.3, labeled Six Sigma perspective. It was originally proposed by a Japanese engineer named Genichi Taguchi, and is widely known today as the Taguchi loss function. Exposing the hidden factory. Very few companies can actually achieve Six Sigma, fewer than 3.4 deficits per million opportunities, or even 5 Sigma, fewer than 233 defects per million opportunities, performance in their final products, because so many critical processes, process activities, machines, people, and materials have to interact along the entire value stream. For example, for System X to reliably yield its intended outcomes, it has to rely on the following chain of factors to operate in sync within certain limits of variation. The chemical properties of the catalyst, which is combined with the base material, which is mixed by the processing machine, which is controlled by the inline gauges, which are operated by John, which is inspected by Sally, packaged by robots, stored in the warehouse, and shipped to the customer. Remembering, too, that before any of this execution, the whole system, including the product itself, was designed by a team of engineers who are by no means infallible. If any one of the many critical activities is compromised or doesn't function to its expectation, risk and error propagate throughout the entire system. The system itself is also an opportunity rich environment for hiding risk and error, because problems arising in one part of the chain actually originate in an earlier part, and tracing the root of the problem is difficult without a quality control system like Six Sigma. Among Six Sigma practitioners, this reality of fixing the results of propagated error is known as the hidden factory or hidden operation. You can almost see the wheels of the hidden factory turning, the rework and cover ups, the hours and days of wasted time in a company of people who constantly correct mistakes. Every time a corrective action is taken, a machine is rerun, or a warranty claim is processed, you incur unnecessary rework. When you accept these events as that's just the way it is, you've mentally hidden all these activities from your improvement potential. Servicing the hidden factory wastes both time and money, a company's two most precious commodities. Six Sigma eliminates the hidden factory and therefore returns precious time and money back to the business. With this realistic Taguchi cost model in place, ask yourself where you want the production of your critical characteristics to be. Out near the boundaries of the spec where significant costs increase, or spread out evenly across the whole range of the spec? Or would you rather have your parts lumped consistently near the target where quality costs are minimized and eliminated? Avoiding the hidden factory. So they have this picture of a line, and under the line is the hidden factory, and above the line is like, normal factory, I guess. So it's got, warranty, inspection, stuff above the line. And then under the line is things like engineering change orders, expediting costs, time value of money, long cycle times, lost customer loyalty, excess inventory, long setups, late delivery, lost sales, working capital, excessive material orders and planning, etc., etc. So, okay. Avoiding the hidden factory. Several research studies have shown that typical companies spend an amount equal to about 25 to 40% of their sales revenues on issues related to poor quality. For example, a company with $100 million in sales probably spends between $25 and $40 million each year addressing the problems caused by poor quality. That estimate may seem high to you. If so, that's probably because most of the costs of poor quality aren't immediately obvious and are often difficult to measure directly. Items like scrap, rework, inspection, and warranty costs are easy to see and account for. But the price tag for unseen quality-related items, such as design changes, material expediting costs, lost customer loyalty, late deliveries, excess inventory, and so on, are much higher than most people realize. They're a hidden factory of quality-related costs, a lot like the bulk of the iceberg hidden beneath the water's surface. Figure 2.4 gives you a visual of these lurking costs compared to the more readily visible ones. Looking at how quality beliefs determine behavior. Simply changing a company's belief system, its philosophy, from a goal-post quality mentality to a Six Sigma on target with minimal variation mentality immediately and naturally begins to alter the behavior of employees for the better. See the earlier section, Discovering the Cost of Poor Quality Curve, Football and Taguchi's Lost Function, for details on these belief systems. We look at some of these changes in this section. Comparing belief systems side by side. When you alter your beliefs about quality to the Six Sigma ideal, you notice a big change in how your organization performs. We compare the difference between a goalpost quality belief system and the Six Sigma belief system in Table 2.1. Table 2.1. Naturally resulting behaviors from quality belief system. So for this table, I will do line by line instead of side by side. So, all right, naturally resulting behaviors from quality belief system. For the goalpost belief system, inconsistency across the range of the allowable window is fostered, whereas for the Six Sigma belief system, consistent performance centered on a single standard or target value is rewarded. Work procedures are continually adapted and improvised in an effort to get parts into the allowable spec window, versus efforts to standardize process performance occur prior to experiencing out-of-spec conditions and are never-ending. Meeting the spec ends individual responsibility and engagement and improvement. Never-ending obligation to continually reduce variation naturally extends up the value stream. Efforts and resources are expended to respectively authorize, justify just out of spec parts. Efforts and resources are expended to proactively identify, understand, and eliminate causes of inconsistency. Focus is on yield, dead-end metric disconnected from the reality of quality. Or with Six Sigma belief system, focus is on capability, a never-ending scale of improvement, mirroring the reality of quality. So here's the table. Let's see if I can get it in focus, and you can just pause. I don't think I'm gonna get much better than that. I guess my camera sucks. Well, you can always just get the book and follow along. As you can see, the Six Sigma mentality's focus on proactive measures and continual improvement fosters a much more successful environment than the goalpost mentality, which simply reacts to problems as they arise. Imagine the drastic differences that begin to occur in your work and in your company with this simple belief change. Its effect is truly remarkable. Journeying from one to many. In this section, we look at the numbers to relate probability to quality. Consider a company whose product relies on many individual components and characteristics that must fit and work together. That company must operate at high levels of quality on a pretty minute scale so that each individual part is up to snuff. For example, the average car has about 10,000 individual quality characteristics, or CTXs. That's a lot of stuff that has to work together. If you work at an automotive company, how many cars do you make? How many papers do you have to process every day? How many materials and supplies do you order and purchase in every month? Millions upon millions, billions. Six Sigma practitioners call this concept of compounding defect risk rolled throughput yield, and we explain it mathematically in Chapter 6. In practical terms, the reality of rolled throughput yield means you have to establish an extremely high probability of success for each individual component characteristic if you ever expect your final products, services, and transactions to be highly successful and defect-free. Suppose that every time you roll a 1 on a die, that's considered a defect. With a 6-sided die, then you have 1 chance in 6, 17%, of rolling a defect, or a 5 out of 6 chance, 83% chance, of success. But imagine that now you have a pair of dice and you roll them both together. Now the chance of success, no defects, is only 69%. We show you how to calculate these probabilities in Chapter 6. With 3 dice, the chance of a defect-free roll decreases to 58%. With 100 dice, you're almost certain to have a defect. The actual probability of never getting a 1 when rolling 100 dice is less than 1 in 82 million. Connecting quality and variation. Whatever probabilities your process has in the short term will change in the long term. Machines, process inputs and outputs, and single characteristics all vary, which cause their assemblies to vary as well. To get a good picture of what your product's overall quality looks like, try visually plotting the associated behaviors and looking at them like a picture. Such a plot helps you see immediately that every characteristic you can measure has a performance distribution. Furthermore, you can plot behavior today, plot it again next week, and compare the difference. Comparing a single snapshot to the accumulated variation over time is an example of the change in behavior from the short term to the long term. Figure 2.5 shows 2 probability distributions for a critical characteristic: short term, solid line, and long term, dotted line. As you can see, in the long term, the variation in the behavior of the characteristic expands. This distribution is a common occurrence. Here's what's happening. The probability of a defect in the short term doesn't account for certain changes that take place over the long term. Examples include the variation among different batches of incoming material, the impact of seasonal road traffic on delivery time, and the different working styles and habits of different personnel. Joe may be a great machine operator, but he can't work 24 hours a day. Eventually, he has to be relieved by Jim, who works a little differently from Joe. Each one has his own performance variations, but combined, they enlarge the range. Short-term variation doesn't necessarily refer to a specified period of time for every time of performance distribution. The time period involved in short-term performance variation for a restaurant meal is different from the period involved in the performance of electricity delivered to your home by a power plant. Chapter 5 provides more detail and understanding on why this discrepancy occurs and what it means for the Six Sigma practitioner. Calculating Six Sigma quality. The term Six Sigma comes from the statistical basis of the approach and methodology used to address the concerns from the two preceding sections: the roll-up of characteristic behaviors and the natural increase in variation in each characteristic over the long term. The Sigma scale is a universal measure of how well a critical characteristic performs compared to its requirements. The higher the Sigma scale, the more capable the characteristic. For example, if a critical characteristic is defective 31% of the time, you say that this characteristic operates at 2 sigma. But if it runs at 93.3% compliance, you say it operates at 3 sigma. Table 2.2 shows a sigma scale. The sigma scale. No good. If a characteristic operates at 3 sigma, that means the variation in its performance exceeds acceptable levels 6.7% of the time. This breakdown may be an invoicing process that goes longer than the company's allowed time limit, a forged bolt that is longer than customer requirements, and so on. Whatever the critical characteristic may be, if it's 3 sigma, it's defective 6.7% of the time, or 66,700 times out of a million. In Chapter 13, we explain more detail on how the Sigma scale is created and why it's called Sigma. What the originators of Six Sigma discovered is that when they worked to have each critical characteristic in the system, the product, the service, the transaction, perform at a Six Sigma level, the risk of the individual characteristics being incorrect was small enough, 0.00034% or 3.4 defects per million opportunities, that the overall system still performed at an exceptional level when all the parts were assembled together. And even when long-term effects inevitably entered into each characteristic, the overall system performance remained high. These companies then had a method for competing at a whole new level on the global market. That's why 6 is the magic number. So why 6 and not 5 sigma? The complex products for which this method originated had enough characteristics rolled together and enough long-term degradation that only 6 would do. 4 or 5 sigma just didn't provide enough relief from these two constraints. The systems and environments of transactional and service companies now adopting Six Sigma are often less complex. They don't have as many critical characteristics coming together, so they don't necessarily need to have each critical characteristic operating at 6 sigma. In these cases, 4 or 5 may actually do. But the magnitude of the earlier success of Six Sigma has made the name stick. And almost all companies, regardless of their size or complexity, recognize the benefits of aiming for a Six Sigma goal. Even if the milestone of Six Sigma is never reached, the act of working toward the goal drives breakthrough changes. In some instances, great companies are able to produce Six Sigma quality in their final products, services, and transactions, especially when safety or human life is involved. For example, did you know that you're about 2,000 times more likely to reach your destination when you fly than your luggage is? That's because airline safety operates at a level higher than Six Sigma, while baggage reliability operates at about 4 Sigma. Table 2.3 highlights quality levels for a 99% quality level, 3.8 Sigma, compared to those for 6 Sigma for some everyday occurrences. Here's that table, if you're able to. All right, and that's chapter 2. I guess I'll read the table to you. All right. Table 2.3, how good is good? 99% good, 3.8 Sigma, or 99.99966% good, 6 Sigma. All right. So for good, for 3.8 Sigma, 20,000 lost articles of mail per hour, or 6 Sigma is 7 articles of lost mail per hour. Unsafe drinking water for almost 50 minutes per day, 1 unsafe minute of drinking water every 7 months. 5,000 incorrect surgical operations per week, 1.7 incorrect surgical operations per week. 2 short or long landings at major airports every day, 1 short or long landing at major airports every 5 years. 200,000 incorrect drug prescriptions each year, 68 incorrect drug prescriptions each year. No electricity for almost 7 hours each month. 1 hour without electricity every 34 years. 11.8 million shares incorrectly traded on the New York Stock Exchange every day. 4,021 shares incorrectly traded on the New York Stock Exchange every day. 3 warranty claims for every new automobile. 1 warranty claim for every 980 new automobiles. 48,000 to 96,000 deaths attributed to hospital errors each year, or 17 to 34 deaths attributed to hospital errors each year. And that does it for chapter 2.